Hello all. Today we're going to be looking at a building of sequences, and when we add all of those together, those are called series. So we're going to be looking at series today. Now, this is kind of an interactivity into that. So let's just say that there's Little Red Riding Hood, and she starts out with there are 16 square tiles. So on the first tile, she drops 2 crumbs of cake. And then on the second tile, she drops 6 crumbs. On the third tile, she drops 18 crumbs. So pretty soon, she's going to like run out of crumbs that she's dropping, 54 here. And so hopefully you start to kind of see a pattern. That pattern being that we are multiplying by 3 each time. So another way that we could write this 52 is, or 54, we could write it as 2 is what we started with, and then we multiplied by 3 times to get there. And that's going to be 2 times 3 to the third. And so down here, if I keep this pattern up on my 6th tile, I'll have started at 2 and I will have multiplied by 3 1, 2, 3, 4, 5 times. So I will multiply by 3 5 times to get there, which is just 1 less than the number of tile that we have. So on the 8th tile, I will have started at 2 and I will multiply by 3, 1 less than that, so 7 times. And then we kind of develop this pattern 2 times 3 to the, and it's going to be the n minus 1 because it's just 1 less. Okay, so our whole goal is to kind of see how many crumbs she's dropped along the whole time. So if I think about just the third tile, that's kind of like in this case, this will be like the third term in my series. I'm going to add together all of the crumbs that she has dropped. So she started dropping, she dropped 2, and then she dropped 6 on the second tile, and then she dropped 18 on the third tile. So if I add all of those up, she will have dropped 26 by the time that she's gotten to the third tile. On the 5th tile, so again, 2 plus 6 plus 18, or I could just start with that 26, and then she also dropped 54 the next time around and 162 the next time around, which is another multiplication by 3. So she's already dropped 242 crumbs by that time. I do not want to do this for the 16th tile. Like, I don't want to add all of those up. So I actually want to do a little bit of a pattern that we would have here. And the way that I'm going to represent this term that I have is S sub 5. It's the 5th term in my partial sum. So I'm going to start out by just grabbing that partial sum, my 5th partial sum that I have there, and then adding together this crazy pattern that we actually had. And so we had 2 plus 6 plus 18, and I'm going to write my 6 as 2 times 3. I'm going to write my 18 as 2 times 3 squared. I'm going to write my 54 as 2 times 3 to the third, and I'm going to write my 162 as 2 times 3 to the fourth. And the reason why I am doing this is I want my term number, so this is my first term, my second term, I want my term number to actually match up and be exactly the number of 3's that I have. So this is my 5th term, and I want it to be 3 to the 5th power there. So the way I'm going to do that is I'm actually going to multiply both sides by 3, and what that is doing now is I'll have 2 times, this is my first term and I have 1 3. This is my second term and I have 2 3's, and so on. Okay, the reason why I kind of did that, and I shifted over this term 5 but multiplied by 3 just a little bit over to the right, and you can kind of see things match up a little bit. What I'm actually going to do is I'm going to subtract these. So I'm going to have my S5 term and then minus my 3 times that S5 term. And then what happens when I subtract over here is I'll get that 2. These will cancel out, these will cancel out, these will cancel out, these will cancel out because I'm subtracting them. And then I'll have a minus 2 times 3 to the 5th. Now, my whole goal here is to actually solve for that s to the 5th. And I have 2 of those s to the 5ths over here. The way to kind of group them together is I'm going to factor them out. I'll be left with a 1 minus 3 when I have that, times 3 to the 5th. And then now to find my s to the 5th, all I need to do is divide by this 1 minus 3. And the reason why I left it as that 1 minus 3 is that that is going to work for any value for n. So before we come up with that value for n, let's actually look at our s to the 5th. S to the 5th is going to be 2 minus 2 times 3 to the 5th, all divided by 1 minus 3. And we can actually start to see what is going on here. So this 3, just like this 3 right here, is my common ratio. It's what I'm multiplying each time. This 2 right here is like my a sub 1. And I can even write this just a little bit even more written out. If I actually factor this 2 out of both of those terms, I'll be left over with 1 minus 3 to the 5th, and you can kind of see that pattern is there on the bottom as well. So this is my ratio, what I'm multiplying each time. This one was my a sub 1 that I started out with, and then this 1 and this 1 are kind of just always there. So if I were going to use that to actually find the total number of crumbs, so my 16th partial sums that I would start out with that 2. I would have 1 minus, my ratio was 3, and then this was my 5th sum with a 5 there, so this is going to be 3 to the 16th power all over 1 minus 3. And it's actually going to be this insanely huge number, but that gives me my partial sums. Okay, the whole point of this is just so that you can look at this formula and you can be like, oh, I actually kind of know where that came from. Miss Atherton actually helped me develop that. And again, this is with a geometric sequence where we are multiplying by something. So this is our common ratio, what we actually multiply by each time. This check your understanding you can use to check your understanding. We're not actually going to look at any of those examples, but again, you can look at that. It's all about partial sums and finding finite summations or finite series. I want to actually jump, so that was a little introduction there, and I want to jump now into what about if we have something that is like an infinite number that we're adding together. So I want us to think about a pizza that is huge, and we cut it into 4 equal parts, and each person grabs a slice. So each slice was just 1/4 of our pizza that we have, but then there's a piece actually left over, and so that last 1/4 that is left over, we're actually going to cut it again into fourths, and then each person is going to get one of those. So Jason, Carrie, Ben, and we're going to have a little one of these left over. So again, this is 1/4 of 1/4 that they're getting. So it's essentially 1/16 of the whole pizza. 1/16 of the whole pizza. And if we actually look at this as a pattern, so 1/4 of 1/4, and then this other tiny little piece right there, that's tiny little piece, it's 1/16 that's left. We cut that in fourths, so that is actually going to be 1/64, or 1/4 to the 3rd. Maybe you have started to actually see a pattern here. My second slice is 1/4 squared, or yeah, to the 2nd power. My third slice is 1/4 to the 3rd. I could also write it as 1/4 to the 3rd because I'm just multiplying that 1 kind of up top. So go ahead and finish out the rest of these. And then we're going to figure out how much total pizza was actually consumed. So our total pizza that is consumed, we started out with 1/4, and then we added 1/16 to that. And then by the time that we got to the third slice, we added 1/64 to that. So here where I have a series, here where I have a sequence, over here, this is my summation of that sequence. So this is actually my partial sums. So I'm adding together all my partial sums. So P1 plus P2 plus P3, and these are my partial sums. So a way that I can represent that is this is like my first term in the sequence plus my second term in the sequence, and that would give me my partial sums of the first two terms in the sequence. So that would be adding together that. And this kind of makes sense too. If the knife was super sharp and we just kept on cutting that last little chunk into thirds, eventually these three people would each get a third of the pizza. Another way of saying that is that my sum of this partial sums, if I add together all my partial sums, from 1 to infinity, I would get 1/3 that I would have there. And we know that this is a sequence that is geometric because we are multiplying by 1/4 each time. And the sum of the terms actually represents the total pizza consumed after the nth slice. And this also kind of makes sense too, because what I'm essentially doing is I'm adding up a small amount. So I'm cutting things into 1/4, 1/4, 1/4, and I'm adding those summations together. So it would make sense for this to have a finite value. Another way of saying that is that our sequence is actually converging. So our sequence of 1/4 to the n power, this as our sequence is converging, it goes to 0. So it would make sense that our summation or series would also converge. And actually I can say that it does converge by using this formula. So this one also converges to the equation that we used from up above. So this is going to be 1 minus my ratio, which is 1/4 right there. And then up on top, I'm going to have my starting out value, which in this case, my starting out value was 1/4. 1/4 was my starting out value. And sure enough, if I actually figure this out, this ends up going to 1/3. Each person is going to get 1/3 of my pizza. Okay, next we're actually going to look at both of these two sequences, and I am going to write my A sub in the first 4 terms of that sequence in blue, and I'll do the other one in orange. So my first term in my sequence is going to be 1/1, which is just 1. My second term is going to be 1/2. My third term is going to be 1/3, and my fourth term is going to be 1/4. Now I'm going to do the same thing with my sequence B sub n, which is, let's see, if I plug in 1, I'm going to have 1/1 squared, which is just the same thing as 1. I'm going to have 1/2 squared. 2 squared is going to be 4. 1/3 squared, so 1/9. And 1/4 squared, which is 1/16. I'm going to open up Desmos, and we're going to look at our partial sums for each of those sequences. Okay, I'm going to start with my 1/n value, and there's a couple ways you can do this. You can type in sum, and it will actually come up with that value, and we're looking for our sums from 1 to, we're just going to look from 1 to 10 of this sequence, 1/n. And so I can do that same thing, and I can look at my values, my summation from my partial sums, my first 50 partial sums, and my first 100 sums that I would have there. Okay, so that's for my sequence 1 over n. Let's look at that for 1 over n squared, my b sub n sequence. So here are my summations, my partial sums for the first 10, the first 50, and the first 100. You can kind of see that they're a little more stagnant for our b sub n, but our a sub n just keeps on increasing. And I want us to think back to when we were covering improper integrals. What are improper integrals are you thinking about? And the ones I'm thinking about are going from, let's just say, 1 to infinity of a sub n versus if I had 1 to infinity of my b sub n or my 1 over n squared that I had there. I'm going to rewrite this in limit notation. So since I can't actually take this integral from 1 to infinity, I'm actually going to rewrite it from 1 to b, and then I'm going to say, hey, my limit as b is approaching infinity of 1 over x. And what that ends up becoming is ln of x evaluated from 1 to b, and if I plug in b, I plug in my 1, and I'm still taking my limit as b approaches infinity, we'll actually see that this part is going to diverge. It's going to infinity. So this diverges. It kind of makes sense then for my partial sums here, my partial sums to also not to go increase towards infinity as well. The same type of thing over here. So if I take my limit as b approaches infinity of 1 over, or 1 to b of this 1 over x squared, which I can rewrite just like this. And I actually take my integral of that. So that would be x to the -1 times -1. Plug in my b, plug in my 1. I'm going to have -1 over b minus another -1, so it'll actually be a plus 1 over 1. And we can actually see, since our b is approaching infinity, this chunk is going to approach 0, and this actually converges. So that's convincing evidence for up here for my partial sums to also reach a stopping point or converge. So another way of saying that is this is actually called our harmonic series, and we can write it as 1 over some value to the p power. Sometimes we talk about this being a p series. So the harmonic series always diverges. 1 over n always diverges. And so it does not have a finite value. But my summation 1 over n squared converges, and in general it's always going to converge if that p value is something bigger than 1. So think about this example up here. My p-value was 2, and so that was actually going to converge. Here are our notes talking about those 3 different sequences and series. So a geometric, harmonic, always diverges, and a p-series. So a little bit of an introduction into those 3. I want you to be able to try these out, this check your understanding, and then there will be an answer key right below. Bye everybody, have a great day.